Thanks, Tim. Thanks, everybody. Good to see you all again today. We're going to have 4 great speakers during this morning session, the Deep Learning and Performance 2 session, 4 20-minute talks, starting with David Ramirez, who's a PhD student and engineer currently at Arizona State in Prime Solutions Group and a Marine Corps veteran who's going to tell us about his work building large language models for synthetic aperture radar.
Thank you very much. They said I have to use the mic, but I'm going to try to just speak loudly. Hopefully I don't blow out anybody's eardrums. We're getting started a little bit early, so I might take a little bit of time here. Yeah, let's get into it. So we want to build large language vision models for synthetic aperture radar. That's sort of what we're getting into here. And so how are we going to do that? Was anyone at the seminary last night with Brigadier General from the AFRL? One of his talking points was AI can improve a lot of technical workflows, including intelligence analysis. And so AI and machine learning have been used for synthetic aperture radar traditionally, but we want to try to solve this question. Can we use the new generation of modern large language and vision models for SAR understanding? And what are the computational requirements to get there? There's been some related work in the last 2 years for remote sensing and geospatial applications. You'll see these terminologies, LLaVA, CLIP, GPT, VQA, used through a lot of these other papers. And so what does that mean? We're going to talk about it a little bit. I'll define those acronyms. We'll talk about where the state of the art is right now with large language models and vision models. But where the shortcomings right now in academic research? Well, it's mostly electro-optical surveillance, focused on land cover, land use. There's very limited work related to synthetic aperture radar. Mostly there is some vehicle classification and ATR, but it's with small foundation models from maybe 5 years ago or previous. And so there's really been no work yet on generative language for synthetic aperture radar. And we think there's a niche there for our research. So our motivation here. SAR is hard. If you're not familiar with SAR, this is an example of a SAR-formed image here. What is that? If you can't tell, neither can I, but it's been a great subject for AI and machine learning research. It's mostly a solved problem, this MSTAR dataset that we're going to be getting into, but it is still a good academic benchmark. There are heavy computational requirements traditionally related to large language vision model, but maybe we can overcome those with some of the modern training techniques. We want to get to a place where, similar to this diagram down here, you can ask any question, an infinite variety of questions to a language model like ChatGPT or like GPT-4 or some of the open source varieties out there, and ask it something related to synthetic aperture radar and be able to get a reasonable response and be able to improve that over time as you get feedback from a user base. And so that's where we want to get to. So a lot of this work began in 2017 with the published paper, Attention is All You Need. I think a lot of people have heard of this transformer neural network architecture. This was improved further through the openly published, not officially published. I think a lot of this AI research is just preprints, people pushing out work really quickly. But this is by the OpenAI company, 2018. And the setup here is, I'm just going to give it a bunch of data and ask it to generate the same data through this sort of autoencoder method. We can give internet scale amounts of text data and just ask it to generate the next token in the sequence. And through this generative pre-training, we've really developed a very capable language understanding method. And these have been known as generatively pre-trained transformers, the GPT, which many of you will be familiar with, synonymous with large language models. I think typically over 1 billion parameters might be considered a large language model. And so using this sort of method here, we're going to take that generatively pre-trained encoder that understands language, understands how to decompose language. We're going to align it with this vision method here. This could be anything. This could be a ResNet model. It could be a vision transformer, something else. But if we can get these two things speaking the same language, then when new images come in, they'll be embedded into the same contextual understanding. And so this alignment step is very important. Next, using all of these methods that have either been generatively pre-trained or aligned to that language understanding, we can build a combined method for language and vision understanding. And so the most popular method here is called LLaVA. I think it's very popular because of its ease of use, its low complex computational complexity. But there are even easier methods to use these days. All of these different things that we're pulling from different places and putting together into this sort of Frankenstein, giant, large language vision model, these might be known as foundation models. And we can build these for specialized applications like synthetic aperture radar or like military intelligence understanding of language. And that's necessary to do so sometimes. Ultimately, we can train all of this as a whole, which is extremely computationally expensive, huge GPU data centers, right, necessary, or we can do some of these modern training techniques called parameter efficient fine-tuning. And so we'll talk about that a little bit. So what are the computational requirements of training some of these types of models? There are a number of neural network parameters in there that are trainable. There might be some amount of minimum GPU VRAM necessary to do the optimization in the mathematics. That might depend then on the amount of GPUs that you have. You'll determine how many GPUs are necessary, and then after some amount of training time, you might produce a model. And so what are the other methods here that we've talked about so far? The attention is all you need transformers method published two different models, a base transformer and a large transformer, this L variety. The GPT-1 that we mentioned previously, these all had hundreds of millions of parameters, which was a lot at the time. They used the largest server cluster of 8 GPUs, and that was the state of the art 5 years ago. And maybe hundreds of hours of training time to make the state of the art model. As the GPT series has grown, they've expanded by an order of 10,000. And instead of 8 GPUs necessary, now we're talking about thousands of GPUs that have been put together in a data center on one GPU fabric, so to speak. And very few tech companies have sort of mastered that method. One of them, the competitor, is the Meta AI Facebook company. And so they've openly released some of these models, the Llama series of open source models. Llama 4 dropped very recently, within the last couple of weeks. And this was advertised, their behemoth model, 2 terabytes, 2 tera trillion trainable parameters, which is even larger than GPT-4. And they said that they have a data center of 32,000 GPUs that are combined. And so that's outrageous, right? A lot of the researchers here for specialized applications, there's no way we're going to get to 16,000 GPUs. But what can we do? These other methods here, the GPT series, these are not open source. We can't pull these models in. We can use them, we can pay for those products, but we can't necessarily train them to exactly our specifications. Similarly, the Llama series of models, they have legal restrictions for use in defense and military applications. But we can use this Minstrel model, a 7 billion parameter model, which the unreleased amount of training on 500 GPUs. We can align that with some of these other methods here, the CLIP alignment that we mentioned previously, the vision transformer large method. Combined, we could call that a LLVA method. And so we use some of these from the open source community that have been combined, this CLIP with the Minstrel. And our method here We fine-tune with quantized LoRa, and we'll talk about that. So we have 4.2 million parameters out of 7.6 billion. And we can do that on one GPU, a consumer GPU, in only 20 gigabytes of VRAM. And so we think that that's a very novel result in only 2 hours of training. So I think many of you here at the ATR conference would be familiar with the MSTAR dataset, produced in 1995, 96, over 3 decades old, but still relevant for this area of research. So this commonly has 8 military vehicle types in the mixed target dataset. We want to expand that. We want to try to make the problem a little bit harder. And so to do that, we're going to combine it with some of the other MSTAR datasets. We're going to grab out 11 different target examples, combine those together. We got 3,000 training images, almost 3,000 test images. And then we want it to generate language. And to do that, we give it these sort of target types, ATR targets, but they've been broken up by character because this vehicle is not in the dictionary of the language model, and so it must combine different letters to create those words. So this is called tokenization, and we'll talk about this a little bit more. It's very similar to classification, except that we're trying to predict amongst all the dictionary elements in the understanding of the model. So for our second experiment, we want to generate longer captions related to the imagery. And so we ask it to predict the vehicle type, as well as some qualifying information, descriptive elements related to the vehicle. And these are longer again, and they're broken up sometimes into sub-words through this natural language processing tokenization. And these elements, one by one, will be generated by the large language model. And there's the possibility for error. And I think people would be familiar with this concept of hallucinations, where perhaps the wrong words will be generated, or the words will be combined in an inappropriate way. And we see that a little bit. And so these are our 2 experiments. Our proposed method. We're going to take that Minstrel 7 billion parameter language model, which has good use, legal restrictions here. We can use it for military applications like this. We're going to take the CLIP vision encoder, which has been publicly released by the OpenAI company. This is a very capable model here, which uses a patch size of 14 little sized chipping elements, and up to a 336 pixel image input. And so any larger than that, there are some methods to sort of break it up, but that's some of the restrictions here. We combine that. We use the LLaVA Next architecture, which combines it into a cohesive language vision model. And then all of that together, the language model, the vision encoder, combined with this aligning projector, that might cost 240 gigabytes of VRAM memory without any tricks. If you were going to try to train that through TensorFlow, PyTorch, whatever it is, that's what you would expect to need, which is maybe 4 top-of-the-line enterprise GPUs. It could cost you $1,000 to do this fine-tuning. But a batch size of only 1 isn't necessarily going to give you great performance. If you would be familiar with machine learning training, you might want to see multiple image examples at once during the training procedure so that you can optimize for multiple cohesive patterns. So how do we get around some of these restrictions? The tricks that we use are quantization and parameter efficient fine-tuning using this quantized LoRa method. So we're going to compress all of our numbers, the neural network weights for our mathematics. The number representations we're going to put into a 4-bit normalized floating point representation. And so we're using a half byte precision when storing these instead of a 4-byte floating point. Next, we're going to do all the mathematics in 16-bit brain floating point, which is a new standard that has been adapted by the NVIDIA compute architecture. And so that allows us to compress instead of large floating point values into a smaller mathematical calculation. And so that further reduces our memory footprint on GPU computations. Then we're going to use the quantized low-rank adaptation. We're going to inject these sort of weights in the middle, and that's how these are represented. We're going to put new trainable parameters into the language model, and we're going to train only those and not the rest of the language model. And so we're going to keep all of the rest of the language model frozen and only train some of these injected weights. And so that's 4.2 million parameters out of like 7.6 billion. And so 1/20th of 1% of the overall architecture is trainable. And so it's a very small, very reasonable amount of training that you have to do. And so together, we can get a batch size of 8 and see 8 image examples at once, and it only costs us 20 gigabytes of memory. And so that's doable by most good GPUs. Okay, and so here are some of our results. On the first experiment, once we got this working, really excited, we did one initial training run. We didn't do any hyperparameter tuning, which you might expect through traditional data science. We got this running. We ran it for 1 epoch. So it saw all of the examples from the MSTAR training set 1 time. Then we started checkpointing the models every 100 training steps. And we wanted to evaluate the performance over time. Is it very consistent with these models that it's generating? We found our best model to have 98%, which is good for the MSTAR dataset. But that's sort of cherry picking. If we can just pick the best model with the a priori knowledge that we know what it's trying to evaluate against, that's sort of cheating, right? And so what we want to have is a reproducible method that every time it gives us pretty good performance. And we're not guessing when to stop training our method. Sure. We train it up until 2 epochs. And the reason that is because if we train for longer, we start to see these sort of hallucinations. We see weird combinations of letters and even things that are not vehicles. If I've got any military veterans, the homies here would know the DD-214. Okay, so second experiment. We did a small Monte Carlo of several models. We trained those for exactly 2 epochs. And then we try to get the average performance. And we're very consistent now. If we can train it for only 2 epochs, it's only seen each training example 2 times. It can give us up to 98% performance, which is great. And that only costs us 2 hours of training time. And the reason is that we're using all of these pre-trained methods that we discussed, these foundation models. And so this is great. You can see how the sequences are broken up by tokens. And so we don't observe any hallucinations in this regard. And maybe that's because there's all this other descriptive language that it's learned related to these ATR targets. But we need to evaluate that claim. So our end goal, here's where we want to get to. 0-shot prediction. So you can ask any sort of question against this large language vision model and get a reasonable response from the model. And we're trying to build towards that goal. We could improve hyperparameter tuning, like we discussed. There's certainly a lot of additional work we could do related to LoRa, perhaps using more trainable parameters instead of the small quantity that we did use. Maybe if we had more compute, we could do that as well. Data augmentation. That's a typical data science enhancement, right? We didn't need to do any data augmentation. We can pursue other things like chain of thought reasoning, generating a lot of contextual information, word tokenization. We want to benchmark against other data sets, other MSTAR methods, see how we do compared to those. We want to get to this goal of visual question answering, and to do that, we're going to build a large data set with these image captioning and question answer pairs, and we hope to release that soon so we can evaluate similar types of models in the academic sphere. So here's our method again, some of our final conclusions. 4.2 million trainable parameters compared to the 7.6 billion. We only need 5.7 gigabytes of VRAM at a minimum, and that only takes 2.3 hours of training, which I think is would blow a lot of people's minds. We think of these large language vision models as unfeasible for most applications, but these modern techniques, I think they can be adapted to new domains. The problem we found was we don't retain the full capabilities of the language model yet. And so perhaps there's a way that we can very precisely fine-tune these things where we can still conduct regular conversations with these chatbots. So I think that's all I've got.